Welcome, guys. Yeah, so this is part of the analysis lecture of the series. Yeah, so previously that we just proved, give a definition, what is the converge series, and also prove the comparison test. Yeah, basically, if you can bound your series, bound each term by another converge term, then you will converge. If you are greater than some diverge term, you diverge. Okay, so hope you guys subscribe to my channel. Okay, so in this video, we should talk about the root test and the ratio test. And this is usually commonly used in the calculus, but in the calculus, we don't prove it, right? But now in the analysis, then we should be able to prove it. Okay, but we prove another theorem. Okay, so this theorem is interesting, which is you can use this to prove the convergence of the P series. Okay, so suppose you have a series, you have a A1 up to A2 greater than equal to 0, basically all of them are positive, and the series and from 1 to infinity converge. So then, if only if 2 to the k, a to the 2k, k from 1 to infinity, basically it's a1 to a2, 4a4, 8a8, to converge. Okay, so this is interesting results. Basically, we say that these converge if we only pick the power of 2 converge, if they are all monotone. Okay, so let's see the proof. Yeah, so let's see a proof. So let's talk about the first thing is Sn, right? Sn to be the partial sum, and also about Tk, basically A1 plus 2A2 up to 2AK, 2 to the K, A2K. Okay. And let's see. So for n less than 2K, so for n less than 2K, we just see the Sn, right? So the Sn less or equal to A1 plus A1, sorry, A2 plus A3. Right, because A2K plus up to A2K plus 1 minus 1, right? So if n less than 2K, then you can bound this, right? Because yeah, right? So this is A1 plus A2 up to A3, right? So Sn only up to An, right? But the n is less than 2 to the K, so I can bound this Sn by add more terms from here to here. And these guys great less or equal to A1, and this is 2 less or equal to 2A2, right? Because at least A are monotone decreasing. So 4A4, A8, 2 to the K, A2 to the K. Okay. Yeah, so what's this? It's just Tk, right? So basically we show that for n greater than less than 2K, Sn bounded by Tk. Okay, so on the other hand, let's see, right? So if n is greater than 2K, that's Sn is greater or equal to A1, A2, right? A plus A3 plus A4, A2K minus 1 plus 1 up to A2K, right? 2 to the K. I think this is the same reason, right? Because if n greater than 2K, then Sn already only add up to the An, right? But in this we only add up to 2 to the K. So Sn is greater than A1, A2, 2A4, right? 2 to the K minus 1, A2K, right? So this is Sn greater or equal to half Tk. Okay, so you can get Sn to Sn greater or equal to Tk. Okay, so basically, so what we have is Sn less or equal to Tk for n less than 2K, and for n greater than 2 to the K, there are 2 Sn greater or equal to Tk. Okay, right, so if, let's say if Tk converge as K goes to infinity, and this is bounded, right? So Sn converge by comparison test, right? If Tk diverge, that means this blows up, right? Become infinity, then Sn blows up, so Sn diverge. Okay, so write down everything Sn converge if only if Tk converge, and the Sn diverge if only if Tk diverge. Okay, so very beautiful proof. Okay, so theorem called P series. So theorem, this is very important. So 1 over n to the p from n from 1 to infinity converge if p greater than 1, if p less or equal to 1 diverge. Yeah, so these converge, these diverge. So if p less or equal to 1. Okay. How to prove it? Okay, so let's see. Okay, so the stupid case is that if p greater or equal to 0, then easy to see that n goes to infinity, right? 1 over np will not be 0, right? If p is negative or 0. Okay, so in this case, the diverge is trivial, right? So diverge is trivial. Okay, so and the second is that by our theorem, right? So let's say p greater than 0, and by our theorem, you can just check. You can just use this tk, right? So this tk. Yeah, so you can just change it to a 2 to the k, 1 over 1, 2 to the kp, right? So it's k from 0 to infinity. So 2 to the k and a2k term. Right? So get k from 0 to infinity to 1 minus pk. Right, so this is the geometrical series. So it converge whenever 1 minus k, 1 minus p, right? This is a geometry less than so this is the ratio, right? This ratio should less than 1. Okay. So 1 minus p should be less than 0, right? So converge. So if 1 minus p is greater than 0, it diverge. So p greater than 1 converge, p less or equal to 1 diverge. Okay, also theorem. What is the case, right? So the theorem says that if p greater than 1, converge. If p less or equal to 1, diverge. Okay, and yeah, so let's prove it. So proof is basically using the same trick, right? So you change it to 2 to the k, and log 2 to the k log 2 to the k to the p 1, right? So it become 1 over log to p. You can pull out this log to p and write it as k from 1 to infinity 1 over kp. Okay, you need to do some algebra, right? But since it's trivial, right? So you get an answer, right? Because it based on it's basically the same thing. Okay. So exercise for you guys. Exercise. How about this? So log n times log n. Is this diverge? Or how about this? Log n log n squared. So the result is this diverge, is converge. And then you can just use the same trick and keep going. Okay. Yeah, so they are very easy to easy to detect. And yeah, there are various sequence series version. It's very hard to determine whether they converge or diverge in general. Okay, so somehow I think in this video we will not touch the ratio test and root test because I want to talk about natural log. Okay, so let's define natural log. Okay, so define. This is one definition. I'm not very like it, but still, that's it. 1 over n factorial. Okay, so now we need to prove rigorous these E exist, right? So basically we need to show that E converge. So basically this series that converge. Okay, so this is trivial. Let's say Sn is we will look in the partial sum. 1 to up to n, right? So this Sn less or equal to less than 1 plus 1 plus 1 over 2 plus 1 over 2 squared, right? So this is less than this, and keep going, you get 1 over 2 to the minus 1, which is less than 3. Okay, because this guy is a geometric series. Okay, so Sn is bounded above. Sorry. bounded above. And what? And the monotone, right? So by a monotone convergence theorem, so Sn exists. Sn goes to infinity. Okay, another theorem basically is commonly used definition. Yeah, so it should be your good exercise for check that how to prove this guy exists. This is not very trivial, right? But we can prove it. Okay, so now we need to prove this to this. So if I define E to be this guy, and I should be able to prove the limit is this guy, right? So everything should be consistent with your calculus. So Sn is let's say 1 from k factorial, okay, from 0 to infinity. Tn is 1 plus n, 1 over n up to n, right? So let's using the binomial expansion on Tn. So you get 1 plus 1 over 2 factorial, 1 minus n, 1 over 3 to factorial, 1 minus 1 over n, 1 minus 2 divided by n, from 1 over n factorial, 1 over 1 minus 1 divided by n, 1 minus 2 divided by n, times up to 1 minus 1 divided by n. Okay, so this is just a binomial expansion. Should be still not so difficult, right? So from here, obvious to see that Tn is equal to Sn, right? So you can take the soup, right? And I already know that Sn converge, right? So let's take a limit soup. Right, so we have this. Okay, so let's say for n greater or equal to m, we can see that Tn greater or equal to 1 plus 1 divided by 2. So what? Sorry, 1 plus 1, 1 2 factorial, 1 minus 1 over n. So this is the same, right? But I only when n greater than m, right? I only cut up to m, right? So I only cut. So I only cut up to this guy. There are a lot of them. 1 minus this. Okay, so what I'm doing is that I change this 1 divided by n factorial into m, right? So I increase this. I increase the final term. So let's see. What's going on? Sorry, this should be m, I think, because there is a typo here. Yeah, okay. Okay, so yeah, so we can take m fixed. Sorry, take m fixed, and then let n goes to infinity, right? So this Tn, right? So up to Ct, and so you get your limit inf, right? Because your Tn now is fixed, bounded by n, right? So limit inf only care about the infinite behavior of your series. So this guy is greater or equal to 1 plus 1 plus 1 over 2 factorial. So this got killed by this, right? So this is Sn. Okay, so you also then you take m to be infinity. So this guy, right? This now become a limit soup, right? So prove that the limit inf that's greater or equal to limit soup, right? So limit soup is also E. So basically you have shown that the limit soup Tn is less than E. So by these two, you can safely say that we already proved that if the limit soup of series and the limit inf of series are the same, then this series is converge. So converge. Nice shot. Okay. And finally, we can just make our simple conclusion. Just change this proof a little bit. We can prove the following. So E is irrational. Okay, so I will prove E is a transcendental in the algebra course, but not in here. Okay. So in the routine, we only prove E is irrational, but in my algebra algebra video, I can prove that it is transcendental. Okay. So how to do this? Yeah, so E minus Sn, right? So this E minus Sn just one, this, right? Just the remaining term up to infinity, right? So this is less than 1 divided by n plus 1 factorial, 1 plus n minus 1, and then 1 plus n minus 1 square, right? So this is just 1 over n factorial n. Okay. Yeah, it's just using the geometry series. Okay, so basically, we have just proved this. Okay, so this equation will make us to prove that E is irrational. Okay, hopefully it's not astonishing. Okay, so proof. So the usual idea, right? So prove somebody is irrational just using proof by contradiction. So you first assume it's rational. So suppose is rational. Sometimes feel like yeah, actually there's a little bit lonely, right? So PQR a little bit lonely for mine is hopefully not wasting time doing some stupid thing. Okay. Yeah, so they are compared to each other, P and Q. So let's take n, right? So from this, let's take n to be q, right? So I should be able to get q factorial e minus sq less than 1 over q, right? Okay, but by definition, this guy is a integer, right? So let's say we get, so this guy is integer. Right? So also by definition, right, your q factorial sq is q factorial 1, sq is this, right? Right, so by you see each term can cancel, right? The denominator can cancel by the sq factor, so this is also integer. Right, so that means this guy is an integer. This guy is an integer. Right, but the problem is there's no integer greater than 0 and less than 1 over q when if you pick up q is large enough, right? So if you pick up q is any integer, a positive integer, right? So contradiction, because no integer which is greater than 0 and less than 1. Okay. So it's rational. Okay, so next proof in a I will check about, I will in the Hurston in my algebra course, I will prove that it is transcendental. Okay, so yeah, we can only talk about this, and next time we talk about root test and ratio test. See you guys next videos.